Hello, welcome to my talk on frame benchmarking and its future, or its proposed future, or more general, my ideas about it. So my name is Tale-Yazdi, and I work at Parity as a runtime developer, and yeah, let's go. So this is Sub0, it's a developer convention, so I assume you at least somehow know what benchmarking is in the context of frame. But I will still go over the high-level stuff so we are all somewhat on the same page. So what is benchmarking? It means to measure a specific property of a piece of code. And this property is just, well, described as effort. And yeah, well, then we can express this effort with weight. That's what we call weight. It's an expression of effort. And the benchmarking then generates these weights. So this is why we do benchmarking to generate weights. And yeah, but it requires specific hardware, which makes it a bit yeah, tricky. Okay. So the current state of benchmarking, since I'm talking about the future, I will start with the current state. So it's currently not automated. It's laborious and difficult to write. So we made some polling with developers, and one of the main pain points that always came up was writing benchmarks. I see a few developers here; they all don't like it. So yeah, understandable. And why do we even need all of this? I mean, if we spend so much effort on it, what's like? Why do we need it? So these pre-dispatch weights are like pre-dispatch in this case means it's the weight before the transaction was dispatched. So we know ahead of time how much weight it will need. And we only do this as a security measurement. That's basically the only reason to keep the chain alive. Otherwise, if it wasn't for that, we could just leave it away and be happy about it. And there's currently no alternative. So yeah, we are basically stuck with this. But what can we do about it? So there are a few I don't know, ideas about it, and one of them is metering. And yeah, this is like the main topic, that metering is a possible alternative. So I will start to explain what it is. By metering, it's similar to benchmarking that we measure an effort, but in this case, it's not measured once in the beginning, but it's rather measured each time that the effort is spent. There runs some counter or whatever, or however we implement it, and it keeps increasing with the effort. So yeah, it's done each time, and in this case, it's dynamic, since with the current benchmarking state, we have these pre-dispatch weights, and they are just a linear formula with multiple variables. And this means that it's always the same for the same transaction. So when Alice sends a transfer to Bob, and she sends that twice, it's going to be twice the effort, and the weight is always constant. But with metering, it will be something dynamic. And then metering still needs some pessimistic limit where it will not go above it. Yeah, it's just, I will go to the requirement next, but there still needs to be some pre-dispatch limit, even if we have metering. So it's something to consider. Yeah, the advantages, I mean, it's quite obvious. It's hopefully fully automated, at least what we envision. It's less codes, less bugs. Everyone likes that. And we should get fee refunds. Currently, these refunds must be done manually, similar to the benchmarking logic, as we have these pre-dispatch weights. And then after the transaction executed, we can calculate the post-dispatch weight. And then the difference of that can be refunded to the user so that they pay a more precise fee, since the pre-dispatch weight is always like a pessimistic limit. But this is currently done manually, so you have to calculate the difference and estimate at the end what's going on. And it's like, yeah, again, laborious and difficult. So with the metering, it would be possible to have this in an automatic way, such that it meters the effort and then refunds everything that was not spent, or instead of refunding only charges what is necessary. So yeah, it would be, the user would pay a more precise price. Okay. So let's assume we can somehow conjure up a metering solution, however, maybe. There are still obviously requirements, so I'll just bring them up. So it must be secure. Secure is like a very broad term, but I will use it in the sense that it should never underestimate the effort, which means that a specific piece of code uses some effort, then the metering should always at least report that. So it should be, never an underestimation. It should be precise, like this is the other side of the inequation. It should never overestimate, and a small overhead, which means that it should have, like when you run the piece of code, it shouldn't take much longer with the metering enabled. Okay. Otherwise, we have deterministic, which means that when we meter something twice, it should still be the same. Since if we import a block later on, we still need to come to the same conclusion. It's quite obvious. And bounded, obviously we have some resource constraints on it, and it needs to always finish with a specific time. Okay, so let's assume we somehow have some ideal metering solution. Now, I think we can start thinking about this before actually building it, just to see what the implications are and how we can mitigate or navigate them. So an ideal metering solution is obviously everything that I said before. It's precise, it's bounded, it has a small overhead. It's just, basically all the requirements. But what I said before, that even with a metering, we still need some kind of pre-dispatch wait, since this is like in the block building phase. When a transaction comes in, then the block builder needs to decide, should I still include this transaction or not with the given remaining resources? And even with metering, we need to have some cutoff there. And so how do we get to this cutoff? I just called it limit here. And how do we set it? So there's like different approaches. We can either set a fixed cutoff for all the pallets, for all transactions in the whole runtime. Or we can set it per transaction type, or per call rather. So that, for example, a transfer would have a different limit than some NFT, like a balance and an NFT transfer would be different. This gives a more granular checks. And then the third one is quite different. It would be dry running. Since with the first two ones, these limits are provided by the runtime developers. And the runtime developers are entrusted the security of the chain. So the limits that they put in there are trusted. Whereas for the third one, it's dry running, in which case we could have the user dry run the transaction and then propose that. So this dry running is kind of like, it differs quite a lot from the first two, since this limit is not trusted, which would be passed in. And then we have the case that the metering actually, so that it takes longer than this than the limit. And this is a case that we currently don't really handle, or would have a very high difficulty handling, since we always had these guaranteed worst case pre-dispatch waits, and now we suddenly have a pre-dispatch wait that was provided by the user and could be wrong. So we then have to handle the case that the runtime somehow notices, oh, it was wrong, I need to backtrace. So I'm just going to go in more detail into this. So for the fixed limit, it's just the one limit over all calls. It's very difficult to arrive at, since how would we define this? So if we look at all the possible transactions in the runtime, and now we need a limit for all of them. Like, I think it's pretty much impossible to know. We would just have to guess. We would say, I don't know, it's like half a block or 70% of a block or something similar to this. But it's only arguably secure, since in order to actually verify that this worst case limit is correct, we would again have to write benchmarks. And this is kind of what we want to get away from. And it has a high upfront cost, since this pre-dispatch, like this worst case limit, would again be used to deduce some fee from the user. And then at the end, after the metering reports the exact value, it would then do the automatic fee refunds. But having half a block or whatever as as fixed upfront cost is not usable, since I don't know, on Polkadot it would be maybe like 8 dot or 10 dot or something in that range. And it would compound for XCM use cases where something goes over multiple hops, and then each time the user would have to allocate these funds temporarily, basically giving the chain a credit, like a one block flash loan credit or whatever, and this then accumulates. So I think this fixed limit is like a bit difficult to get right. And wait, I'm just gonna go back. I thought there was another slide about the per transaction limit. So for the per transaction limit, we can set it more precise, but it's still like the first 2 points of the guesswork and the arguably secure still apply. Whereas for the high upfront cost, it would now be better, since we could set a worst case for a transfer with balances, for example, and a worst case for another transaction, like an identity update or whatever. And so we would have less wasted upfront cost. So for the dry running, as I mentioned before, it differs quite a lot, but we have at least twice the effort. And we actually, when we build this metering solution in a way that I hope we do, then we only have twice the effort. But there's a very large other ecosystem where this is actually done differently. They work with transaction reversion, and it works by executing a transaction with a specific limit, like a resource limit. It's called gas in that case. And when it runs out of this gas limit, then it reverts. And what they then do is they do a binary search. They first start with a full block, run the transaction, and if it doesn't revert, then they go with half a block, run it again, and this way they can do a binary search and run the transactions very often just to find a precise cutoff for when it doesn't revert anymore. Now, I hope we won't have to resort to this, as it's not just twice the effort, but logarithmically with the size of the block. So it's, I don't know, maybe you would have to run it 10 times, and then we have 10 times the cost for running a transaction. That's not good. On the other hand, we have less upfront costs, and since the user could first dry run the transaction locally, then provide this rather exact limit, and then the chain would refund the small difference that there still is. But for dry running, it requires the full state, and this makes it a bit restrictive. Either you have to keep the state locally or need some kind of RPC node that can be queried. But the state items, it could be a lot or it could be larger items, in which case it's not really that easy to get working on low bandwidth devices. So, now to some of the implications of ideal metering, as I hinted before. So this is about MEV, about minor extracted value. I hope most of you have heard of it. Otherwise, I will give a short explanation. I mean, so with MEV, it means that block producers, in this case the miners, can extract some value from the ecosystem, but while still staying within the freedom that the protocol grants them. So it's not an exploit; it's just a smart use within the constraints. Specifically, it means normally it is done by reordering transactions in an order that benefits the block author. And if you do ideal metering, then we can also do MEV stuff, since the weight isn't constant anymore like it was before, but it is now dynamically determined. And that's the reason why MEV becomes possible, since now, just to give you an example, so if Alice sends a transfer transaction and she sends it twice, and before that she would have to pay exactly twice the price, since it was just twice the effort. It sounds very obvious, but with metering, if we do the proof size metering as well, then the second transaction would be cheaper, since the accessed state is already in the proof. So the first transaction would pay for the proof size, and then the second transaction would pay nothing for the proof. So in this case, we would then have some kind of transaction price, which is quite different to what we have now. We just have a fixed cost. But with a transaction price, we could then have cases where L2 services or off-chain services are built that monitor the blocks and see when is like a good spot to include a transaction, and only then send this transaction because it would be cheaper in this case. So we would have some kind of not gas price. I mean, it could also be called gas price, since in the end the effort is measured in weight, or rather weight price. So yeah, I think it would be quite different from what we have now. And we also need to give second thoughts to block utilization, since so far there's no MEV, and with MEV the block utilization gets like a bit, I don't know, difficult, or it just needs more thought. I mean, now the block producers could include or exclude specific transactions or reorder them however they want, just so that the user pays more or less fee, and it produces some weird incentive and structures that we currently don't have in the protocol, and just makes all the security analysis more complicated. And then there would obviously be some secondary market, since now the second transaction that Alice would send when she sends the same twice would be cheaper. So the block builder could now say, I will not include this in this block unless you tip me, so or bribe. Let's call it bribe me. So there would be some secondary market for this tipping infrastructure, so that Alice in the end still pays less for both transactions, but the block producer gets some part of this less. Implementations. I don't know what I wanted to write here. Sorry. So more implications, I guess. So more resource usage in this case. As I said before, it's run twice, or at least twice. It means that we have more resource usage per transaction, and that is not free in itself. If we just economically assume that any project has a fixed number, a fixed amount of funding, then having more resource usage just forcing a transaction is like less efficient, so they can have less transactions with their funding. But in the end, it's not like we aren't taking this money from nowhere in this case. Before that, it was just used for developer cost. Since currently people have to write benchmarks, so the cost is spent for having developers write benchmarks and order to code. But now we can trade this off with instead using metering, which has more resource usage in itself, but thereby you have less developer cost. So it's something to be considered, and I think there's some fine lining that we can lay out and recommend so that it's still working. Okay, but so with this metering, it's all fine and well, and you want to use it, I see it. I mean, I also want to. But why can we not just, once we have the ideal metering, why can we not just start using it for everything? Like, do we still need the benchmarking? And I think we need. For example, there is code currently in the code base that cannot be metered because it relies on the specific property that the effort is known in advance. And this is, for example, for hard deadline code, which is code that always must execute in a block. So there's no way this code cannot execute. If it doesn't, then the chain just halts. So this is what we call hard deadline code. And for this code, we need to know in advance how much work can be done, because it cannot be reverted. And this means that we cannot use the metering. We still need to meter these tasks that we have, and then know how in advance how much effort they will take. So we are doing this, for example, in the scheduler and in the message queue palette. The scheduler palette just has an agenda for each block, and it then checks the agenda, and it checks how much weight do I have left, and how many tasks can I fit in there, and then it starts to only use the tasks that still fit in there. Now, if the runtime could handle like a panic, then we could maybe get around this, but currently it's not planned. But yeah, maybe there could be an escape hatch. Yeah, so for this code we would still use benchmarking. Since I just wrote it again in the last point, it needs pre-dispatch weights. Okay. So since we still need the benchmarking for some parts, but we also still want the metering, we can like do a hybrid solution in this case. So we just benchmark the stuff where it doesn't hurt a lot to benchmark it, to still profit from the efficiency that it gives us. For example, for simple transactions, I think it wouldn't make much sense to actually meter a balance transfer, since it's very simple to write a benchmark, and like the developer cost is spent on that is not high. Verifying that it's correct is also not high. And we also benchmark this hard deadline code, which is normally just everything that runs in on initialize and on finalize. It's two specific hooks in the code, but most of the code base isn't called from there. And then for complex transactions where it would take rather long to even mentally understand what is the slowest path, we can leave them to the metering, and there's some inefficiency, but just spending all the time on finding the slowest path would, in this case, probably not be worth it. Sure, this kind of depends on the exact thresholds for the inefficiencies. So if the overhead of the benchmarking, I mean, I would assume people are fine with something like 20 to 50%, and then still use it, even if it gives them, like if it gives their users less for their money. So, but yeah, it's a trade-off as everything. Okay, so now to a different approach. This is like a whole different approach. I have like 3.5 minutes left, but it's something that was just very recently talked about. It's fuzzing. I mean, sure, fuzzing was talked about before, but in the context of benchmarks. So it's proposed alternative number 2. And what fuzzing does is it takes a piece of code, and the requirement is that this piece of code takes some input, and then it alternates the input and always checks how long does it take now. And just the standard approach of brute forcing it is not what we would want to do, or what anyone is doing since 10 years. But there's a measurement called like AFL, like American Fuzzer Loop. Yeah, I think that's how it's called. And what it does is it inserts some introspection into the compiled code to check the branch coverage, to check all the ifs and match statements in the Rust code, and then ensure that it hits all of these statements. And by doing that, we can actually find the slowest path, since we can then check that all of the paths were covered, and then just select the lowest one. And currently, this selecting of the slowest path kind of has to happen in the developer's brain, like manually. They need to think about, okay, what is the slowest path? What do I write a benchmark for? Sometimes we write multiple per function because we don't know, or there's an if in the code. But then this fuzzer, I mean, hopefully it works, and we can use this. Would automatically find the slowest path for us. Yeah. But oh yeah, right. So it would be fully automatic. There would be no manual benchmarks needing to be written, and we still have the advantage of the pre-dispatch weights, so we can use it in all hard deadline code and everywhere where we need high efficiency. So to come back to the trade-off, before that we traded off developer cost with efficiency, and now we trade off developer cost with running this fuzzing tool, since this fuzzing tool could take a while until it finds the slowest path. When there's a lot of arguments and a lot of state, we also need to fuzz the state that code touches, and if there's a lot of it, it could take, I don't know, I mean, maybe a day or whatever, just a guess. But yeah, this would be the trade-off in that case. Yeah, downside is we don't have any prototype, so it's just thinking. Yeah. So for the current work, since there's no prototype on fuzzing, we are working on metering for POV clawback. This is basically 50% of the metering. So the metering is like 2 parts, one for the time component and one's for the proof component, and this one would be for the proof component. I don't know if you can access the slides later, but it's a pull request by Sebastian, who is implementing this currently. And yeah, I hope we can use this. It will give us better efficiency over manual benchmarks. And then for WASM metering, I mean, currently we're using WASM, and for the time component, it's basically on ice as far as I know. There wasn't any progress. So this is a bit difficult with WASM, but we have this new hope of RISC-V. I'm not sure if you saw Alex talk today. And there's a forum post about Polka VM, which is using RISC-V, and hopefully we can get this a bit easier done. Okay, so vision slide, I will skip that amount of time. It's basically just a recap. But then, okay, hope you enjoyed.